All right, so this problem is a continuation from last week of the optional problem. There was a pulley problem there. This one adds one level of complexity to it in that there's friction. Last week's one had no friction. All right, so it says a block of mass 4 kilograms is at rest on a table. The coefficients of friction between them are mu static equals 0.30 and mu kinetic equals 0.20. A string connects the block to a hanging mass as shown. A, what is the minimum mass for the hanging mass to make the system move? And B, once it moves, what will the acceleration be? Okay, so right now the system is at rest and the hanging mass wants to pull, like it wants to fall down, and when it tries to fall down, since it's tied to a string, it will also try to pull the block on the table towards the right. However, it might not move it because the friction between the block and the table might be too strong to make it move. So there's lots of ways I can approach this, but I'm going to try to approach it in maybe the easiest way to understand. So I'm going to do some pre-work here. I'm first going to find out the value for the maximum static friction. I'm going to have to maximize my space here as well, so I'm going to use this little space in the top right. Yeah, so I'm going to find out how many newtons of static friction must be overcome before that block is going to move. And that can be done with the formula for friction, using the static coefficient times the normal force. Now the normal force for the block, it's going to balance with the force of gravity. Okay, we have another one of those situations where the normal force is balanced with the force of gravity. And we know that the force of gravity is mg. Okay, so I'm calculating mu times m times g. So I'm going to get that value. Okay, I just got to grab my calculator to do that. That gives me 11.76 newtons. And I'm going to underline 2 sig figs. All right, so basically, for part A, how much hanging mass is required to start the whole thing moving? Basically, the gravity that's going to pull down on the hanging mass has to overcome 11.76 newtons. All right, so I'll write that down. Fg for the hanging mass must overcome the static friction, which we just calculated, which was 11.76 newtons. All right, so the force of gravity I know is mg. So mg for the hanging mass must be bigger than 11.76. And I know that g is 9.8, so something times 9.8 has to be bigger than 11.76. So I can figure out the specific value by dividing both sides by g. So divide by 9.8. So calculator again. And that gives me 1.2. Okay, so that hanging mass has to be at least 1.2 kilograms in order to make the system move. It can be bigger than that, but that's the minimum mass. All right, so I'm going to go to part B now. Once it moves, what will the acceleration be? So we're going to assume that we did attach a 1.2 kilogram mass. And now it's moving, it's going to accelerate. So when it moves, the friction switches from static friction to kinetic friction. All right, when it moves, I'm just going to say friction becomes kinetic. So, to get the acceleration is the net force divided by the mass. However, the mass I'm talking about is going to be the two masses put together. So I'm going to call that m total. All right, it's not just the block accelerating, and it's not just the hanging mass accelerating, it's both of them accelerating as a result of these forces. So we got to put the total mass in to Newton's second law equation. All right, the net force. So I'm going to switch to magnitude mode now. The magnitude of the net force is going to be the force of gravity of the hanging mass. This is getting messy here. The force of gravity of the hanging mass, take away the force of friction, but now it's kinetic friction, of the block. Okay, and that's very important to make those distinguishments, because the gravity of the hanging mass is what's driving the system to move. The gravity of the block is not helping the system to move, okay? It's being counteracted by the normal from the table. So it has no effect on helping it move. Whereas the friction, well, only the block experiences friction. Yeah, the hanging mass does not experience any friction. Okay, so in this formula here, I had to be careful to specify what gravity am I talking about? What friction am I talking about? Okay, so the gravity, so I'll just keep going here. The gravity of the hanging mass is going to be mg, 1.2 times 9.8. And then the friction of the block, now it's kinetic friction. So it's going to be the kinetic coefficient times the normal force. And I'm going to skip a couple of steps. The normal force I know is equal to the force of gravity on it, which is equal to mg, which is equal to 4 times 9.8. Okay, I did that stuff up here, the same kind of thing. Okay, divided by the total mass. So the total mass is the mass of the block plus the hanging mass, 4 plus 1.2. That's going to be 5.2. All right, so when I calculate that out, that's going to give me the answer for acceleration. The mu kinetic, I know the value for that. The value for that's given way back up in the question, 0.20. So I'm going to throw all that into the calculator now. Actually, you know what? I'm going to show you this with one extra step. So 1.2 times 9.8 gives me 11.76. And then 0.2 times 4 times 9.8. Calculate that. That gives me 7.84. And then the total mass is 5.2. Okay, so as you can see, the force of gravity is bigger than the frictional force. That's unbalanced forces, so it will accelerate. And when I calculate that out, it will give me the answer. And I'm coming up with 0.75. Okay, so that's how you do this kind of problem with a pulley with friction included. And we can take it up another notch by adding an applied force into it. So that's something I'll do depending on how much time we have during the class in a regular year, but this is not a regular year. I'm not going to throw that in now. This here is already an optional thing. But yeah, we can add an applied force in to increase the level of complexity. So maybe instead of the hanging mass pulling things down, maybe we can have a person have an applied force pulling left on the block. Okay, an applied force pulling left on the block, and that's going to drag the hanging mass upwards. So that's another type of question. And another, like even one more layer of complexity, which I'll do in grade 12, is if the table is not horizontal. Okay, so instead of having a pulley at the end of a horizontal table, we can have a pulley at the end of a ramp, and a ramp is on an incline. Okay, and that's more complicated, and that's a grade 12 thing. The last lesson will talk about ramps though, but without a pulley. Okay, so just a ramp by itself.